Welcome all to this week's ultra-high density editions of the IAS Princeton Joint Astrophysics Colloquium. Today, we'll get to hear from Iair Arcavi. He's an associate professor at Tel Aviv University. He's the sagacious director of the WISE Observatory and a perennial luminary in transient astronomy. So, although he's nominally an observational astronomer, he has previously held positions at the Kavli Institute for Theoretical Physics and was a NASA Einstein postdoctoral fellow. So I can think of nary better person to tell us about transient astronomy at the IAS. So please join me in welcoming Iair to tell us about stars disrupted, destroyed, and coalesced.
Thank you very much. It's a pleasure to be here. It's actually been 12 years since my last visit, so too long. Okay, so the three main things we study in my research group, I had the over-ambitious plan to want to tell you about all of them, and that is not going to happen. Okay, so we're definitely not going to get to talk about neutron star mergers, but you've probably heard enough about those anyway, so you're welcome. We're going to start with tidal disruption events, and hopefully we can talk about core collapse supernovae before time's up. And the reason we study these very different phenomena, of course, is because of the physics and astrophysics that they can teach us. So I hope I can convince you that these are phenomena worth studying. So my story with tidal disruption events starts actually 10 years ago, where we identified a new class of transients, all of which occur in galaxy centers. They were all very blue, 10 to the 4 Kelvin. They were all very luminous, more luminous than a typical supernova, and they all showed features in the spectra that we hadn't seen in any supernova before, namely very broad helium-2 emission, and many of them also showed broad hydrogen, which we had seen before, but these were all quiescent galaxies that were not forming stars, and we didn't expect supernovae there. And so we had this new class, and the interpretation is these are the disruptions of stars around supermassive black holes. So for every star in a supermassive black hole, there's a radius at which, if the star reaches that radius, the tidal forces from the black hole will be stronger than the binding forces of the star, and the star will get disrupted. So if a star is somehow put in an orbit where its pericenter's distance is smaller than this tidal radius, it'll get disrupted. Okay, and this is denoted by this beta parameter, just the radius, the ratio between these two radii. You want it to be larger than 1 for the star to get disrupted. However, we will also talk about cases where the star can get disrupted if it's not larger than 1. And the idea here is, if the star gets disrupted, you might see a flare of accretion, and this would be a way to reveal the 90% of supermassive black holes that are inactive and that we have no other observational access to. So this is a great tool potentially to study the supermassive black hole population. Okay. The other thing, though, you need for this to happen, for you to see something, is for the pericenter radius. You want it inside the tidal radius, but outside the gravitational radius, the Schwarzschild radius, because otherwise you won't see anything, right? All of the action will happen inside the event horizon, and you don't see anything. So you want to be outside of that. And it turns out that for a sun-like star, this will happen if the black hole is less than 10 to the 8. For a non-rotating case, you can push this limit up a bit if the black hole is rotating, but keep in mind that you should only see these tidal disruption events for black holes up to about 10 to the 8 and not beyond. So remember this number, it'll be important later. The last thing you need to know, these events are rare, about 1% or 0.1% of the supernova rate. In top of the fact that they happen in galaxy centers, which are harder to detect transients in just because they're more luminous. Okay, so what will actually happen when a star is disrupted? And these problems are notoriously hard to model. This is my keynote model of a TDE. This is Martin Rees's cartoon from his 1988 paper. Okay, so there's a little bit more information here already. The star comes in a parabolic orbit. Half of it, okay, on zero energy, half of it is imparted energy and escapes. The other half gets negative energy and has to return to the black hole on various orbits. So the material is returning to the black hole, but it's on these elliptical orbits. And then somehow, some magic happens and it forms an accretion disk, okay? And then this accretion produces radiation that we're expecting to see. These are some more modern simulations of this process. Athena is a very important tool here for these things. Where you see it's quite a messy problem. So you're seeing the star being, the material being ejected, the material being close to the black hole. These different scales are one of the things that make this very challenging to model numerically. You have vastly different scales. And so this is very hard to discern. But the original picture was you'd get some accretion going on, and this will produce emission. And in order to do that, though, you have to dissipate energy, right? Because the star, after disruption, it gets some negative energy, but it's still on a very elliptical orbit. And in order to circularize and accrete, you have to lose energy somehow. And this was thought to happen in the apocenter, so pericenter, where the material is squeezed through pericenter, produce some shocks. These shocks dissipate energy and it'll accrete. Okay, so then what we expect to see is emission from an accretion disk, which should emit mostly in the X-rays. And this is exactly what we did not see 10 years ago in the class I showed you. Okay, I should say that the rate that the material falls back onto the black hole, just from Kepler's law, okay, if you take a star and you impart equal amounts of energy to the different mass elements of the star, you'll get stuff falling back at a t to the minus 5/3 rate. So we actually saw that, and it was in the center of galaxy where you expect the supermassive black hole to be, but nothing else about it matched what it was supposed to be. Okay, so the temperatures you expect X-ray, you're seeing optical in UV. The tidal radius for a sun-like star is of this order. The black body radius we measured in our events was 2 orders of magnitude larger. You say, okay, forget about the details. Just count how much energy you have. It's 2 orders of magnitude too low from what you expect when you throw a solar mass star at a black hole with 10% efficiency. This has been known called the missing energy problem, and we'll get back to this later. Accretion disks should have evolving temperature. These events show pretty constant temperature. This is another way we tell them apart from supernovae. They are, tens of thousands of degrees Kelvin for weeks or months. Supernovae can also get this hot, but they cool within days. These things do not cool, and the fact that we didn't see hydrogen in a third of the events is very puzzling because, most stars should have hydrogen, so why should we not see it? Okay, so this is one of the main puzzles to this day. Why do tidal disruption events emit optical and UV light? And we've had a few ideas that people suggested. This first idea is that you do form an accretion disk, but you saw how messy the problem is. There could be some material around the accretion disk which reprocesses the X-rays and produces optical UV at larger photospheric radii, which explains what we see. So you'd have a radius for the photosphere for the continuum, which would be much larger than the tidal disruption radius. And then the lines that you see, hydrogen and helium, would be formed at different locations in this emitting material. So this actually would predict the temperatures, the radii that we see. And then you see here, so these are kind of spectral models. The profiles are put in by hand. It's just really the intensity, the line ratios that are being modeled here. And this changes as you decrease the size of the reprocessing material, because hydrogen is formed way out here where it's cool enough that it's not fully ionized, right? Deeper inside, the hydrogen is ionized, you won't see any lines. So if the extent of this photosphere, if this material is smaller than where hydrogen needs to be produced, you will see 0 hydrogen, so for the smaller radii. And if it's larger, you can turn the hydrogen on and off while keeping the helium, which is formed deeper in, on all the time, which really matches what we see, because we always see the helium and we sometimes see the hydrogen, sometimes don't, at different ratios. And not only that, we actually, okay, this was from 2016. 6 years later, we're finally able to compile some observations on the strength of hydrogen versus the black body radius of this supposedly reprocessing material. And you see kind of a correlation where indeed the radius is larger, you see more of the hydrogen lines, and when the radius is smaller, you see less, which is exactly what was predicted.
How are you deriving that radius?
This is just from a black body fit to the continuum. Yeah.
And the lines are it's just pure kinematic broadening that you see there.
The line profiles are strange. They are not purely, okay, we don't know if they're purely kinematic. There are some ideas that this could be a lot of electron scattering wings going in there. So even directly deriving some Doppler velocities or something from these lines is not trivial. I will say already that we are desperately lacking modeling of these spectra. And I will show you more of this desperation later. The other interesting thing is we do see, I forgot to say, I'm sorry, but we do see X-ray flares from galaxy centers, which match the naive expectations of an accretion disk. Okay, and this now is explained, you already saw in this diagram back here that the reprocessing material need not be spherically symmetric because there could be some openings over there, some funnels. And then this is another picture which says, okay, if the reprocessing material is not spherically symmetric and you're looking for this direction, you see the events we're seeing in the optical. If you were happen to be looking in this direction, you'd see directly into the disk and you would see the X-rays. And sometimes we see them and sometimes we don't. Yeah.
Some of the early models predicted that peak of the spectrum would actually be in very soft X-ray, extreme UV, which is a part of the spectrum that's difficult to observe.
Yes.
Can that be ruled out, and could that account for some of the missing energy?
Absolutely. Absolutely. It happens that these things, as you say, peak in an area where we can't see, so we don't actually know where all the energy is. We try to infer it, sorry, from the Rayleigh-Jeans scale of the spectrum that we do see, but there are a lot of uncertainties involved in that. And one of the ways to know if we're missing a lot of energy in that regime, so the missing energy is coming from, our extrapolation of the black body, but we could be wrong about it. We could be missing some energy there. One way to probe it is through dust. If this energy heats dust, which is then released in the infrared that we can detect, we can try and account for that energy. Okay, so that could ameliorate the problem, yes. So this is one solution, which seems very nice and very appealing, except there's a problem. This is a simulation already from 2006. You're going to see the star get disrupted. There it goes. Half of the material is ejected, half is coming back. And remember, in order to form that accretion disk that we need to see it being reprocessed later, we need the material that's coming back to lose energy and circularize. And the idea was that it would happen right around here in this nozzle shock where the material is squeezed. You could dissipate energy, but these models, these numerical models show that you actually do not dissipate, you do not dissipate enough energy there. The material keeps going around in a highly elliptical orbits. And so it was claimed that that nozzle shock will not dissipate the energy you need to circularize and form an accretion disk. Okay. But what will happen is GR precession. And so the material that's coming back around the second time is slightly in a tilted orbit compared to the material that came back the first time, and it's going to collide out here at apocenter and create these shocks out there. So because they happen out there, we call them outer shocks. Okay, so you didn't dissipate a lot of energy here, but these outer shocks do dissipate a lot of energy, and it was calculated that in fact they would dissipate energy that would turn into the emission that the temperatures that we see and the radii that we see. Plus, this would be the mechanism that the material would later be able to form an accretion disk that supposedly we haven't seen yet in the optical events. Okay, so this was a completely different picture, saying, no, you're not seeing the accretion disk, you're seeing the process of losing energy in order to form the accretion disk, which could be years or decades later, or months, right? Okay, this wasn't exactly determined. These are more modern simulations with Athena++ that confirm this picture. And they say that the shocks created out here are likely the dominant emission source, at least up to peak luminosity. But in addition, that these also create strong outflows that could later form the basis for that reprocessing material that will reprocess the accretion disk later. So perhaps we're actually seeing both, right? We're seeing at early times, the emission is dominated by this mechanism. At late times, we're going to form an accretion disk and it's going to be reprocessed by the material that this same mechanism produced. I know Alex has some reservations about this mechanism. This is not a solved problem. Okay.
And roughly how much luminosity do you have in the great phase? It's still observable at 6 hours and at 25 hours, as it does cool off. But
yeah, so it actually doesn't cool off. The temperature stays very hot for months. And it decays. And what we're discovering now is that late times, years later, we see these plateaus in the UV, which that we think is directly, okay, not directly, but you're seeing the accretion disk after all of this mess is over. It's a much cleaner picture. These late time plateaus are showing an accretion disk eventually.
all this speculation is observable and constrained, that's what you're saying.
Yes. Yes, unfortunately, okay, I'll get to this in a second. Okay. This is a very recent simulation that has now shown us something new. This is 3 snapshots in time, and let's focus on the right column, which is energy dissipation, and look at that. This is the nozzle shock, and this simulation now says actually you do dissipate quite enough energy in the nozzle shock, not enough to circularize, but enough to start the circularization process, and then these shocks that, okay, the picture I showed you before was that you dissipate nothing here and the material goes back way over here and shocks out here. These are kind of intermediate shocks because you start circularizing from the nozzle shock and then you produce these shocks somewhere more inside and you produce the accretion disk later. And one interesting testable prediction of this is that this energy dissipation should emit X-rays. Okay, and then the optical will be coming from whatever happens here. Now, the problem is it's very hard to discover an X-ray flare preceding an optical transient because until recently we didn't have wide field X-ray telescopes until Iair. And Iair saw exactly this. Here's an optical TDE, and right at the beginning it had this X-ray flare, which okay they claim could be coming from this emission, this dissipation mechanism here. Now you'll know this happened a year before this paper, but this was actually a prediction because the simulations predicting this were on the archive before this paper stuff. It was actually a very nice prediction, and we still, okay, it's still rare. We still don't have this kind of X-ray data preceding optical flares, but hopefully, okay, I don't know what's going to happen with Iair, but at least Einstein probe maybe can help us with this.
What's the physical difference for, these two different conclusions, the outer shocks versus the string disk?
That is the question. How do we, okay, the physical difference is where do you dissipate the energy? How, on what time scales? How quickly do you circularize?
I guess how well motivated are the different choices?
Yeah, so I guess it depends what simulation you look at. Let me summarize really the different choices now, and so I can answer your question better. So we had this problem that the naive picture told us we should see X-rays, and we asked the theorists, but we see optical, and they came up with not 1, but 3 reasons why we should see optical. Either we're seeing the reprocessing emission from the accretion disk, and this explanation kind of ignores the problem of how do you lose the energy to get there in a way that you won't see it, right? Because they're saying everything you're seeing is from the accretion disk, so you'd have to lose energy in a way that you didn't see. Or you lose almost nothing in the nozzle shock and you lose everything in the outer shocks, or kind of an intermediate thing where you lose some here and you lose the rest here and you circularize. And what you're seeing is the energy loss from these processes here. Okay, so it looks like we're seeing a mix of things. And then my challenge as an observer is what can I do to discern between these different scenarios and figure out what's going on? Or my intuition is that usually when nature has more than one way to do something, it does some combination of them.
But these two things happen for different orbital parameters or different viscosity in a cylinder?
This is okay, so this is like 3D GRMHD radiation, but for one case of a solar mass star around a 10 to the 6 solar mass black hole evolved up to peak luminosity, and that's it. And the simulation
specific eccentricity and everything.
Yes, exactly. These simulations are very expensive and hard to run. We're very far from exploring the phase space. Okay, it's a single scenario.
Many people would say that the nozzle shock is not at all resolved in the 2D simulation, and so that there are concerns that it may artificially dissipate for that reason.
Yes.
This is still that, in some sense, back to Amir's question, that's the big theoretical uncertainty.
And another complication, of course, is I call spin.
Yes.
We looked at this with an undergraduate. So returning material can be torqued into a different plane. So it takes a lot longer.
Exactly. If on top of this a black hole is spinning, the returning material will actually not collide with itself. It'll miss itself. And depending how thick it is, it might take a few orbits to collide with itself again. Yeah, the picture gets even more complicated.
There's a few seats up front for those who would like to take here.
Okay, so the question is, what can we do as observers to try and constrain this? So all of these models were kind of made so that they explain the observations we have seen until then. So we should try new types of observations to see if we can discern them. This work by graduate students in my group, Sarah Faris. I think it is the most detailed observed optical UV tidal disruption event. This is the light curve. The lines on top tell you the spectra, which I'll show you in a second. So once you start observing these things very densely, for the first time, we see some interesting features in the light curve, like a sharp change in the rise slope here and some bumps at the beginning. I admit you kind of have to squint to see that there, but you don't have to squint to see it here. There's another case where we see a tidal disruption event with not quite periodic bumps on the way down. This is the one I showed you before. Here you also see another one with a bump on the way down. And then this one, after we thought it was over, kind of came back. This one, we've never seen any light curve like this. And this was the first tidal disruption event discovered by a new survey we're part of, BlackGem, which was on my title slide. And then this case, which I'll get back to, was a very normal, smooth, nothing interesting about it TD, except 2 years later it happened again, which obviously is not expected to happen. Okay, so I'll talk about this one in a second. But so we're trying to understand, could these different bumps in the light curves and changes in slope and something.
So just to cut, you've offset the light curves by a couple of mags. We're not really getting up to fifth. They're around.
No, yes. Sorry. I'll show you a plot with the offsets later. Yes, this should be stated. Oh, it is. There are.
If you read
very small. I'm sorry. I'm sorry. Yes. It doesn't reach those luminosities. So maybe this structure in the light curve, just at 0th order, could tell us there's more than one emission mechanism going on at the same time. And we're seeing some complicated combination of these processes. Looking at the spectra, where I told you I will showcase our desperation for models, these are spectral series that we have. What you're seeing here is the H alpha luminosity go up and then decline. This is compared to a sample. This event, again, I think is the best observed. It's also the earliest we ever have data. And so for some of these cases, the peak in the hydrogen lags the peak in the continuum by days or weeks. Sometimes they're simultaneous. You're seeing here the width of the hydrogen line kind of go down. And the interesting part is you're seeing the offset of the hydrogen line. It starts right where it's supposed to be, and then it very rapidly shifts to several thousand kilometers per second blue shift and slowly makes its way back to the central wavelength. And so what is going on here? This is obviously telling us something important about the dynamics, about the emitting material. We're lacking the models to actually test this. Okay, so this puzzle still exists today. I think it's the biggest question about these transients. Before we can start using them to probe supermassive black holes, we need to understand what we're seeing, okay? And could it be a combination of these things? Would be my bet, but we still don't know, okay? A second very interesting puzzle, my favorite puzzle about these events actually is not the emission mechanism, but where they happen. Okay, so obviously they happen in galaxy centers, but when you look at which galaxies they happen in, something very funny comes up. So this is a phase space of galaxies. On the y-axis, we have H alpha emission. This is basically a tracer for a current star formation. Okay, on the x-axis, we have H delta absorption. This is a tracer for star formation that happened a few 100 million years ago. Because this is made by A stars. So if you made a bunch of stars 100 million years ago, the dominant population today is A stars, and you get these strong absorption. So most galaxies, these gray points are SDSS galaxies. Most galaxies are star forming up here, and then they slowly stop forming stars and they go down here. But there's this corner of phase space where you have galaxies that are not forming any stars today, but did form a lot of stars a few 100 million years ago. So these are post-starburst galaxies. And when you plot where the TDs happen, this is a plot from a while ago now, but there are more newer plots that show the same thing. They like to concentrate in this corner of phase space where you have less and less galaxies. So they show a very strong preference for post-starburst galaxies. And the further you go to the right here in H delta, the fewer galaxies you have, but more or less the same number of TDs. So the enhancement rate, the further you go, like in this area here in this box, it's like 2 orders of magnitude more TDs than you'd expect. Slightly over here, like in this box, it's 1 order of magnitude, 10 times more common than you'd expect. Okay. And then, yeah, here you don't see almost any TDs. So the question is why?
Is that as expected?
No, this was completely surprising.
No, not the excess, but you say in the normal scale.
Oh.
Are you seeing about the expected rate of TD?
So no, even before this discovery, there was a problem that the theoretical rates were about an order of magnitude larger than the observed rates of TDs. This problem has made it worse. because now if all of the TDEs you're seeing, which is still not enough, are here, there are even less than you expect in normal galaxies. So this has made this discrepancy even.
If you've got all nuclear transients on this, not ones that you're calling TDE, what distribution?
Okay, so this is the strongest, you get the strongest effect when you really choose your sample to the class I showed you on the first slide based on its helium and all of that. You start getting, there's a whole zoo of nuclear transients, which I'll say a word about. You start getting it more spread out. The effect gets weaker, but there is a different, you can look at it differently. And if you look at a more wider class of nuclear transients, you do see that they have a preference for the Green Valley galaxies. So looking at it a different way, they do like Green Valley, and this specific class of transients really like post-starburst. Okay, the more you mix in, the weaker the correlation becomes.
Any observational selection effect in this?
Probably. Probably some observational selection effect. So it could be that the post-starbursts are just the tip of the iceberg, right? And in starburst galaxies where we can't see optical because it's all dust obscured, maybe there's a TDE party going on and we're just seeing, right, the tip of the iceberg. So we've looked in infrared and we found some infrared transients that are only visible in infrared in ongoing starburst galaxies. But it's not enough to explain this overabundance. So part of it could be observational, but the most of it is intrinsic and we don't understand why.
There's also stellar mass, right, that maps into this. The vigorously star-forming things are low mass,
Yes,
which will make it very hard to find a black hole thing.
yes, yes.
And you can't get the big
Right,
galaxies.
and we're limited on the other end.
So I think having a stellar mass cut would probably be helpful.
Yes, you're right. Okay, so there have been numerous explanations. I don't really have time to go into them, but I'm happy to talk about them later. Could these post-starburst galaxies be post-merger galaxies still harboring a binary black hole that would increase the rate of TDEs? Turns out this doesn't work out with the ages since starburst of the galaxies and the rate you'd expect from that phenomenon. Our leading explanation was that these galaxies, these post-starburst galaxies, have a high concentration of stars in the center. And this could be causing a higher TDE rate. This explanation was shut down last week by a paper on the archive, which I have yet to study in detail. But the idea is that if you take into account strong interactions between stars in the centers of galaxies, then actually those are rare, but they're strong enough that it would actually lower your rate of stars getting captured. So now, not only does this not work, you have to explain how, despite having more concentrated nuclei, these things have a higher rate and not a small. So we've gone backward. It also killed our second favorite explanation about a triaxial potential there that could be causing these rates to go high. There have been suggestions about nuclear eccentric disks, but these form and increase the TD rate well beyond what we see. Okay, so that's not a full explanation. At least something else has to be going on there. There could be pre-existing AGN disks in these galaxies, and stars interacting with the AGN disk would have a higher chance of later getting disrupted. This is something that's actually hard to test because I told you it's hard to find transients in galaxy centers. It's even harder if it's in a center that's already active by an AGN. Weeding out the TD there, we definitely have observational biases against that. So that's still a question mark. Okay, but I think this puzzle is still alive and kicking. Why do optical TDs prefer post-starburst galaxies? And this is telling us something we don't know about dynamics in galaxy center. Okay, then this new phenomena that popped up in the last couple of years of supposedly repeating tidal disruption events. This is the first case called Assassin 14KO. It had bursts every 100 or so days. However, for those of you who are keen on spectra, these spectra look very different than the ones I showed you before of the class of things I call TDEs. These are much narrower lines. They look a lot more like an AGN. So to me, this is not a standard necessarily a TDE that's repeating. What is it? I don't know, but it's not TDE.
It's a statement that is periodic with those.
Yeah, with a slightly decreasing period. Yes. Elliot has thought a lot about this event. Itai, okay, yes. Can talk to you more about it. Okay, a second case, this one was kind of a TDE. It repeated in the X-ray and in the UV, not in the optical, but originally its optical light curve was a bit weird and its optical spectra were not bona fide TD class. I'm known in the community as a TD purist. I'm very serious about what I call a TD, and this did not fit exactly the definition. So again, interesting case, but not 100%. This one was thought to be very promising, had two flares separated by a couple of years. The second flare was definitely, there's my broad helium 2, okay, stamp of approval on this one. It was definitely a tidal disruption event. It even happened in one of these post-starburst galaxies that was way at the edge of the plot. Okay, but there was no spectrum of the first flare. It was an order of magnitude different luminosity. And when you go to these galaxies, you now have a non-negligible chance of seeing two unrelated TDs within a couple of years, now that we've seen like 50 or 100 TDs ever. So you do the calculation, you get like 1 to 10% chance that these would be unrelated TDs, and without the spectrum of the first one, it's hard to say for sure. Okay. Now, my favorite case. This is work by former postdoc of mine, Lydia Makrigiani. Already in the name, it was telling us this is going to be a double TD. This one had a first flare in early 2022. It was such a vanilla broad helium TDE. We had no idea what to say in the paper, right? We're like, just this is another TDE. It's not even worth publishing. 2 years later, it happened again. This is flux space. Okay, so about a factor of 2 fainter. You're seeing here both flares shifted. Each band is shifted, but the same for both flares. Okay, so the empty symbols are the second flare, the full symbols are the first flare. You see the second one being slightly fainter than the first and a little bit different up here in the UV. But relatively similar timescales, relatively similar luminosity, and this galaxy was not at the far edge of the plot. It was a post-starburst, but it was in the region where you expect two unrelated TDEs within 2 years of each other at a much lower chance, less than 0.1%, that these are two unrelated TDEs just from that. If you look at the spectra, the top two here, the black and the blue, are the peak, the first peak and the second peak of this TD, and they sit exactly on top of each other. And for comparison, I'm showing you like other TDs, so just you know what the population varies. So remember, I told you some have no H alpha, some have strong H alpha, some have weak H alpha, right? This one had exactly this amount of hydrogen, and the second flare had exactly the same amount of hydrogen. Here's the broad helium 2. Here's again the hydrogen luminosity as a function of time of both flares of this event compared to the population. It's actually the weakest hydrogen we've detected, but it's pretty much the same for both of them. Similar widths for both of them compared to the rest of the population. Similar offsets for both of them compared to the rest of the population. These two flares, spectroscopically at least, looked really identical. Right. Okay. So you could say, well, it's the same black hole disrupting them, right? So, or actually, if you were referee number 1, you have said, it's the same black hole disrupting them. Maybe it's a black hole that's setting the spectral properties, and it could be two different stars, and you would never know. So we know that the black hole, there is no correlation between the hydrogen properties in a TD and the black hole mass. Okay, it's not correlated with the luminosity in TDs. It's not correlated with the width of the line. So it's not likely that the black hole, at least itself, is the one deciding what the spectrum of a TD look like. We're saying it had to have been the same star on the same orbit disrupted twice. Yeah.
But there was discussion about the amount of spin the black hole has can impact what ends up happening.
Yes.
So that might fold in.
Yes, that's true. But we're saying that it would not, we don't think it would create two such identical TD spectra compared to how we know the population varies if the stars were different stars, different compositions, different orbits, not related to each other. Okay, we're just saying that would be very unlikely.
Could you have the same star with partial disruption
Yes.
in each time?
That is exactly our interpretation. Our conclusion is that this had to have been the same star that was disrupted twice. How can the same star be disrupted twice? It has to have been a partial disruption. Remember, I told you you want that beta greater than 1, so you're inside the tidal radius. Well, stars aren't uniform spheres of matter. You can be outside, the tidal radius is just an average radius if your star were a uniform sphere where it gets disrupted, but it's not like if you're on this side, you don't get disrupted, and you're on this side, you do. Obviously, it's a continuum, and if you're outside that radius, your envelope, for example, which is less bound than your core, can get disrupted, or part of the envelope can get disrupted, so the star survives to come again and do it again. Okay. So this could explain why we're missing so much energy. We're not throwing a solar mass of material at the black hole. We're just disrupting maybe a tenth of a solar mass or less. Okay.
How are you getting the black hole masses here?
Sorry?
In this plot, how are you getting the black?
Oh, from the host galaxy scaling relation. Yeah. Independent of the TD. Okay, so this is the energy, the total energy in a sample of TDs is this histogram, and this one repeating event is here. So it's kind of on the low end, but it's not like an order of magnitude lower than, okay, it's not like completely outlier to the population. It is an order of magnitude lower than the peak here, but 10 to the 50, 10 to the 51 ergs is typically what you get integrated out of a TDE from what we see. This is on the low end, but it's not crazy. Okay, what is a bit different about this, the two flares, again, I'm showing you here the bolometric light curve. Filled black is the first flare, empty is the second, and this is a comparison sample. Bolometric light curves are pretty typical. Here it's normalized to peak, so you can just see the decline rate. There's a range of decline rates. And the first flare was much sharper declining than the second flare. These are some numerical models I don't really have time to get into, but just to say that also this plot is cheating because it's showing you mass fallback rates from a model compared to observed luminosity from observations. Those things are not necessarily very directly tied to each other, but just to show you that partial disruptions are supposed to decline steeper than full disruptions. And that kind of matches what we see in both flares.
Can you say a bit more about just how these bolometric luminosities are derived? I mean, what's the typical spectral energy distribution?
Yeah, so
How
it's
do you extrapolate beyond the observed points?
Yeah, so typically we see a black body that we don't quite get to see the peak of, and we fit a black body temperature to it. We do use UV data. If you do optical alone, it's very difficult because you're really on the Rayleigh Jean scale. From the UV, you start to see the peak of the black body, and you can better constrain the temperature, and from that, the luminosity.
With data for this? Or?
Yes, absolutely. Yes. Okay, so it could be that the first flare was a partial disruption and it declined much faster, which is kind of expected by models. And the second flare was the full disruption and it declined much slower. I'll just say a word about how do you get the star into this orbit in the first place. The time between flares was 700 days. You need to put a star in a 700-day orbit around the black hole. That's not something you can easily do with a single star. This is one dynamical scenario to get this, made by Tai here. What you're seeing here is a phase space of pericenter distance and semi-major axis. So these are circular orbits where pericenter and semi-major axis are the same. Here is a semi-major axis for the orbit of 700 days that we need. Okay, and the idea is this star was not on its own. It was part of a binary that came in. The binary got disrupted by the black hole in the sense that one star is captured and one star is ejected. This is known as the Hill's mechanism. These are the typical orbits of stars captured via this mechanism. So depending on the separation between the stars and the binary. So if our binary had this separation, it would be put on a 900-day orbit, which would give you the right semi-major axis, the right orbital period, but unfortunately it'd be too far to get disrupted itself. This is the tidal radius of this star. So you have to get it down to this pericenter distance for it to be disrupted. And one way you can do that is with two body scatterings. And then it would bring down the pericenter distance without changing the orbit, and you'd get this 700-day repeating TD. Yes.
Is there a space where the secondary star would not be completely ejected by the Hill's mechanism, but falls back as well?
Itain.
Probably not. Like, most likely scenario is that this binary was initially very loosely bound. Right? So if one star gets bound and the other gets unbound. Right? So you need both stars to initially be.
But I'll say for the dynamicist here, this is only one. We did not fully explore all the different ways you could put a star there. This is really only one scenario. We just want to say, okay, there is a way to do it, but you guys have fun. The other way to do it. Okay, so this case to me is a very interesting case because there are two options of what's going on here. Either the first flare had to have been a partial disruption, otherwise we wouldn't see it flare again. The second flare, which was slower declining, could be the full disruption, okay? Or it could be partial again, and we'll see a third one. Okay, so we'll know in early 2026 is when we expect the third one. Okay, so there are two options. We see a third flare or we don't. If we don't see a third flare, that means that the second flare was a full disruption of the star. Fits nicely with the declining rate, but you notice the total energies are very similar. The spectra are nearly identical. How can a partial and full TDE look almost the same? And it also means our sample of events might be completely mixed. Okay, and these are two slightly different physical scenarios that produce exactly the same thing. If we do see a third flare, that means they were both partial disruptions. Okay, and since they're so similar to the rest of the population of these events, could they all be partial disruptions? Just we haven't seen them come back yet, because maybe they're on 20-year orbits and we've only been seeing these things for 10 years. So are all of them partial disruptions? And we've actually been numerically modeling the wrong thing. So I think we'll know in early 2026 which one of these is correct. And I think either way it's really okay. Yes.
What's your prediction?
I don't have one. See, because I think this is interesting and this is interesting. So I'm fine. I'm okay.
I'm gonna go.
It's not going to be boring
I'll
either
go on the
way.
record saying yes.
You're saying it'll be a third. Okay.
Is it possible that, was this object observed in 2020?
Yes. So we have.
Do we know that it didn't flare?
Yes. I think I have. Yes. So you see, we have all these limits here from before. It didn't do anything in the years prior. And then this is, yeah.
Well, actually, what does theory predict in case of an empty loss curve? Things get out onto orbits that are capable of disruption by small increments.
Mhm.
It might
Yes.
be that when the first encounter the black hole, we've got well inside there. Disruption.
Yeah, it would gradually come in. Yes. Elliot's actually, and Itai have a.
But
Working.
that's one way to get partial disruption, but most of these stars will be on a 10⁵ orbit, so you don't see them repeating.
Hmm.
So to actually get the repeaters, this Hills mechanism is probably the dominant way. And then the ratio between the full disruptions and the ones that repeat has to do with the fraction of binaries of the radius of influence. So maybe 10%. I would say that the implication of this repeating is not necessarily that all TDEs are partial disruptions, but possibly, there's a decent fraction, maybe 10% that actually are repeaters.
Right. Yeah.
But would you,
I got this.
I was just gonna say, well, all could be partial, but not repeat, but a small fraction.
yeah, and then we don't know.
And are they,
Right.
are all, let's say if you look at all TDE light curves, are they consistent with that extra, more rapid fall off?
So they're spread out. You can see it a little bit here. This is the first flare, which was consistent with the partial disruption. This was the second flare consistent with the full disruption, and kind of the population is right in. Yeah.
Asked about
Would you
this.
then expect a second disrupt, a second, third disruption?
Yeah,
Do you see anything repeating more than once?
we have not yet seen anything repeating more than two flares.
And do you have enough time lag?
Well, for this one, which is my most robust case, I think I'll let you know in a year and a bit.
And the other case, you don't.
The other ones, I think also still haven't reached the
You still
stage
have
where
not
they should
reached
be.
it.
Yeah.
Aside from.
This is super new.
14 KO.
Yeah, 14 KL, the first one I showed you, which is every 110 days, but that's something completely different. The flares are different, the spectra are different.
Could you go back to your light curve? Because it doesn't really look like it's a slower decline. It just looks like there's less of a peak.
So if you look at the different bands,
Not this one.
the bolometric one. Right, yes. So you're right. The question was this just a flatter peak and now they're doing the same thing? Or if you normalize to peak, this one's definitely going slower than this one, which is kind of what this plot is supposed to show, that you can't really tell. This is what you expect, at least for the mass fallback rate, if they were both partial, and it kind of fits. And this is what you expect if the first was partial and the second was full, and it also kind of fits, because it really depends how you normalize.
You also said that they had almost the same emission, but it does not look like this from the bolometric. Like,
So there's a factor of 2 in the bolometric peak. Okay, this one is fainter. There's about, this looks at, okay, depends where you measure the peak, but yeah, there's a factor of a few in the bolometric peak, yeah. Yeah, the spectra are identical. The light curves are a bit different.
Presumably you can share some PDFs for the inferred slopes and say they're the best fits are different, but.
Yeah, the other problem is for the first one, we didn't really catch the rise, so it's kind of hard. Yeah, so the data are not good enough to tell us exactly what are the slopes of the different cases. This is why I think we'll know when we see the third, if we see a third flare.
Why it's 2 years? Can we infer the distance for the star from the central black hole from this 2 year period?
So what is the?
That the period is 2 years.
Yeah, okay, we want the pericenter to be at the tidal radius close to it, so that sets that. And once you know the pericenter and you know the period, you get the semi-major axis, so. Okay, so you can just read it off here, right? It's a few times 10 to the 15. Okay, so new puzzle. Are all optical TDs actually partial disruptions, or do partial disruptions and full disruptions make exactly or very similar flares to each other? We will know the answer to this question in early 2026. Either way, we have some work to do, okay? Need to explain either of these. Now, you can say, given all these puzzles, why do you think these are TDs and not something else, okay? Nothing seems to fit. Okay, so remember I told you that TDs are supposed to produce observable flares when the black hole mass is up to 10 to the 8. Beyond that, the star is swallowed whole, you don't expect to see anything. So if we were to plot the rate of TDs as a function of black hole mass, we should see a sharp drop at 10 to the 8. It's exactly what we see here. Come on. Okay. There we go. Okay. This is the first work to have shown this. This is a more modern, this is a more newer work with a larger sample, but both show the same thing. Black hole mass, rate of TDs, there's a sharp drop around 10 to the 8. I told you can push, it's not a very definite drop because this depends on the spin of the black hole and obviously the mass of the star. But overall, you see this drop, which is sharper than whatever the underlying population of black holes might be. It's much sharper than that. You see that also in the newer data, which has more events.
So the density of galaxies is about 10 to the minus 2 per cubic meter. Wait a minute. I mean, this is the rate per Colloquium volume. Can you translate this to the rate per star galaxy?
He has the black hole mass function.
Yeah, but this might be normalized.
I'm sorry, I'm wondering about another question, which I failed to ask earlier. When you see these, the hosts are dominated by these, let's say, is the absolute rate for those galaxies higher than theory? Never mind the fact that you don't see the events.
Right.
Are they? Is it above 10 to the minus 4?
So we haven't actually measured the absolute rate in those galaxies because of many observational issues. We only measured the enhancement in those galaxies compared to other galaxies. So you need to assume some fiducial rate to get the absolute rate.
But here you've got a rate per.
Yeah, sure, Jonathan has this rate, and I'm trying to remember how he calculated it, but there must be a lot of assumptions going into normalizing this y-axis here, which I don't remember now what they were.
This plot's from 2018. So does it include any of the featureless TDs, which seem to come from galaxies with SMBH masses inferred from sigma that are above this?
Right. So again, yeah. So there's this class of TDs where you see no spectral features, and this features TDs. So I do not know what to make of them. They were definitely not included here. They might be included in this newer paper. I don't remember exactly how they chose this. Okay. We're definitely not going to get to talk about massive stars, but I just want to take the last minute to tell you, okay, forget about all the problems with TDEs. You can still do science with them because you have a light bulb turning on in the center of a galaxy. You can use it to study the environment of the world, and there are two ways we're doing that. And both are being done by this graduate student, Megan Newsom, who I'm remotely advising. She's at UC Santa Barbara and submitting her thesis this week. Supposed to be, okay. So she was saying, yeah, okay, whatever is happening, you have an excess of emission that's illuminating the central regions of the galaxy. Let's use that. So, here's the tidal disruption event. I told you things are very hot. We were always focused on should we need to get UV data and blue data. She actually got infrared data, which we usually neglect, and saw this second peak happen, months after the first peak. And this is interpreted as a dust echo. So the main emission has heated the dust.
So by UV, you mean IVAN?
By infrared, I mean, yes, near infrared, yes, this is I band, yes, very near infrared, but even that we had kind of neglected, yeah. And turns out you shouldn't, because interesting things happen and you can, okay, in very model dependent, kind of infer some parameters of dust, but this is sub-parsec scale at these time scales, which is very neat.
Is it really true the GR data don't show that
Yeah,
at all?
no, they're very smooth and it's only the I band that bumps, yeah, it's a very distinct, distinctly separated in wavelengths.
So dust is getting heated quite a lot then.
Yeah.
Yeah.
Yeah. There are cases also where this has been seen years later. Okay, this, I should say, this has been seen before where there's a infrared excess years after. This is the first time we saw it like very shortly after. While the optical TD, not for this one, unfortunately, but we have a plan for the future to get JHK in.
Just want to point out the implied R minus I color of that thing is going to be pretty strong.
Yeah, it's in the paper. I don't have it here, but yeah. The other thing you can do, and I'll almost end with that, is look at these high ionization coronal lines. So this is a tidal disruption event. It's hard to see because the spectrum are squished because of these narrow lines, but this is the broad helium I told you about. And you see high ionization coronal lines change in time during the TD, and these are interpreted as a light echo of the TD. And this also gives you some diagnostic of what's the material around and how it's getting ionized. I don't want to go too much over time. I'll just say this is the tip of the supermassive black hole transient iceberg. We're seeing events with narrow lines, which have lines of something called the Bowen's fluorescence mechanism. So we call them Bowen's fluorescence flares or BFFs. We've seen one changing look AGN accompanied by a flare that kind of looks like a TD while the optical goes up and down, the X-ray goes down and up. And we've seen in front of our eyes, it turning from a narrow line to a broad line AGN on a few months time scale. This is the width of the lines going up. We've caught it in the act for the first time. So you'll say, great, LSST, Rubin is going to find a ton of these, which is true. But will we know which ones they are? Because if, first of all, only about 10% of ZTF transients get spectra. And of those, if you only look at galaxy centers, only about 2% are TD. Everything else is usually a type 1a supernova. Even less of that is these Bowen fluorescence flares. You can do a bit better if you look only at blue events. You can do much better if you look only at close starburst galaxies, but there aren't that many of those. So it's still an issue of a needle in a haystack that we have to find. Two ways we're going to try and solve it in the coming years. New spectrograph, if you're interested, talk to me about Son of X shooter coming up online next year. And
on which telescope?
The NTT in Chile, the 3.5 meter telescope in La Silla in Chile. This will be dedicated to transient spectroscopy 365 days a year. But I think the main revolution, and I promise I'll end with that. You can say, well, I told you that supernovae cool within days or weeks, whereas TDs stay tens of thousands of kelvins for months. So just wait a month and you'll know which one's a TD and which one isn't, but that's too late. Okay, we want to find them earlier. So you can just go bluer, right? Don't wait for them to cool to 5,000, wait for them to cool earlier. And we're going to do that with Ultrasat, which is an Israeli-led space mission. 200 square degree field of view UV imager in space. It's going to find 1,000 TDs a year. And we will know within day 3 or 5 or something, if it's still UV bright, it can't be a type 1a supernova. And then we'll get all of them, right? We'll catch them all.
UV means 300 nanometers. 200 nanometers. How blue do you have to go?
How blue do you have to go?
How blue can you go?
Yes, so this one's like 150. Yeah.
How
if I
blue
remember
can you
correctly.
go? Can you do it from the ground?
Challenging. Yeah, I mean, the less blue you go, the more you'll have to wait to tell the difference between the two populations. The bluer you go, you'll know sooner. Yeah, that's the idea. Okay. Definitely no time for corporate supernovae, so I will just leave my summary. Okay, so I told you about tidal disruption events, biggest puzzles, what is the emission mechanism, why post-starburst galaxies? We're finding new repeating events, structure in the light curves, we're mapping spectral light evolution and supermassive black hole environments. Here is everything I did not tell you about massive stars, but I will tell you over lunch about an asteroseismology of massive stars that we're doing. And yeah, feel free to talk to me also about what I didn't even try to tell you, which is gravitational wave follow-up and all the surveys and tools we're involved in. And this is, of course, all work of an excellent research team. So thank you very much.